We'll now begin section 7.2, where we will discuss the sum and difference identities. We're going to begin by taking a look at an example that shows why the sum and difference identities are important. The first problem that we're going to work asks us to determine the exact value of sine 75 degrees. Now, what they are asking is that I work this problem out, not entering it into my calculator. If I think about the tools that I have so far, I know that I have the sine values for certain angles, but those angles are angles that lie along the unit circle. 75 degrees is not one of those angles on my unit circle. And so we need to determine a different way to work out a problem like sine 75 degrees. So we introduce the idea of the sum and difference formulas for the sine, for the cosine, and for the tangent. Now I'm going to go ahead and show you those formulas, and then we'll look at how we apply them for our first example. Notice that we have a sum formula for the sine. That's going to be this one, the one that takes two angles and adds them together. Our angles are u and v. We also have a formula for the difference of two angles. So sine u minus v is going to be the difference of two angles. We have similar formulas for the sum of two cosine angles and the sum of two and the difference of two angles when we're taking the cosine. And we also have formulas for the sum and the difference for tangent. So let's go back to our problem. So the idea is that we want to be able to take the problem that we're given, sine 75 degrees, and we want to break that 75 degrees up into either two angles that are added together or two angles that are subtracted. Now, you want to be careful about the angles that you select. And obviously, there are many choices that we could make, but some choices are better than others. For example, I could say that 75 is 50 degrees plus 25 degrees. But the problem with that selection is I don't know anything about sine 50, and I don't know anything about sine 25. So in effect, I've picked two angles that are no easier to work with than the original problem. What I want to try to focus on is selecting two angles that appear along the unit circle. So one option would be to say that 75 could be written as 30 degrees plus 45 degrees. This is a better choice because I do know that sine 30 is 1/2 and sine 45 is square root of 2 over 2. And so I'm using angles that are on the unit circle that I have information about. Now, in order to work the problem, we have to go back and get our formula for the sum of two sine angles. And so what I'm going to do is I'm going to pull this formula to the other slide, and we're going to look at using that. So this formula says that the sine of u plus v is equal to sine u times cosine v plus cosine u times sine v. So in other words, for our problem, the u is going to be 30 and the v is going to be 45. And so our formula is going to look like this when we plug the angles in. Sine 30 times cosine 45 plus cosine 30 times sine 45. Okay, so let's go ahead and write that down. So I'm just going to copy this over. Sine 30 times cosine 45 plus cosine 30 times sine 45. Now, the next step is to actually evaluate each of these expressions. So to do that, remember that we have a chart. I'm going to flip to that chart for just a second. If you don't have this written in your notes or printed out, you probably want to do that so that you can quickly identify these angles and these values that we need for the problem. All right, so I know that sine 30 is 1/2. And I know that cosine 45 is square root of 2 over 2. I know that cosine 30 is square root of 3 over 2. And I know sine 45 is square root 2 over 2. Now, notice that I have gone ahead and taken the values in the chart and rationalized them when necessary. So, for example, the cosine 45 that I'm using is the rationalized version of this. Okay, so back to our problem. Let's look at what we have. We want to do some simplifying. This is multiplication here on our first two terms, so we're going to multiply those together. So multiplying across the top, we'll have 1 times the square root of 2. Multiplying across the bottom, 2 times 2 is 4. We'll multiply our second set. Square root of 3 times square root of 2 is square root 6. 2 times 2 on the bottom is 4. All right, and so our final answer is going to be, I'm going to push those fractions together, square root of 2 plus square root of 6 over 4. Now, it is easy enough to check this to be sure that what we have is correct by using our calculator. In your calculator, you can evaluate sine 75. And if you do that, you get 0.9659. And then you can also go to your calculator and type in the answer that we came up with. And assuming that we have things correct, we should get the same answer. And so these are easy to check because you do have your calculator and you can be sure that this matches this. Okay, however, they are not going to want you to give your final answer in decimal form. You would want to write it in a form similar to what we have here. Okay, so let's go ahead and look at a second example. We're going to look at determining the exact value of cosine 195 degrees. And so again, we need to determine two angle values on our unit circle that can either be added or subtracted to give me 195. Now, there are lots of choices. I'm going to go ahead and use, in this case, a subtraction, just so that we can see how the subtraction works, since we did an addition in example 1. So I'm going to say that 195 could be written as cosine 240 minus 45. Now, again, there are plenty of other options that you could use. You just want to be sure that you are selecting two angles that appear on your unit circle. And those two angles can either be added to make 195 or subtracted to make 195. All right, so now that I have my two angles selected, I'm going to go back to my formula and let's see how this is going to look. So we're going to be using the difference formula for cosine. Our first angle is going to be 240, so that will be our U, and our V is going to be 45. And so we'll plug these in. And so we're going to have 240 for the first cosine and 45 for the second. And again, 240 for the first sine and 45 for the second sine. And so let's go and we'll write this down. So we have cosine 240, cosine 45. Remember, the sign in the middle was a plus. Sine 240, sine 45. Okay, so let's start looking at our values now. So 240, we're going to need to use a reference angle for that. And so think about where that angle actually lies. So 240 is going to be, that's 180, and we'll need to go an additional 60 to get to 240. So remember that your reference angle lies between the terminal side of the angle and the x-axis. So this 60 degrees that we went to go from 180 to the angle, that 60 degrees is our reference angle. All right, so I need to remind myself that cosine of 60 degrees is equal to 1/2. And furthermore, that my signs for cosine is positive in the first and fourth quadrant and negative in the second and the third. And since our angle lies in the third quadrant, then cosine 240 will be a negative 1/2. All right, cosine 45 is a little bit easier. That is square root of 2/2. Sine 240, we're going to have to do the same type thing that we did with the cosine. We're going to have to come over here and use our reference angle. Remind ourselves that sine 60 is square root of 3/2. So we know that that'll be the value here, but we have to decide, is it positive or negative? And so remember that with the sign is positive in the first and second and negative in the third and the fourth. So again, we're going to have a negative on that because our angle lies in the third quadrant. And then sine 45, again, it's a value that we can get very easily, square root of 2/2. Okay, and so let's work this out. So we're going to have a negative 1 times the square root of 2, which will be negative square root of 2. 2 times 2 will be 4. On our second set, we're going to have negative square root of 3 times negative 2, which will be negative square root of 6. 2 times 2 will be 4 in the denominator. And so again, since these have the same denominator, we can sort of push them together and make one fraction. We can say square root of 2, negative square root of 2. This negative on the square root of 6 will become a minus. And we'll have 4 as our denominator. Now, just as before, it is wise for you to go to your calculator and check to be sure that these two expressions are equal. So when I put in cosine of 195, I'm going to get negative 0.9659. And then when I plug in the expression that I came up with, I also get negative 0.9659. And so you want these two to be the same, and that gives you some assurance that you have done the problem correctly. Okay, so we've done a sine, we've done a cosine. Let's go ahead and look at a tangent problem. All right, the question says determine the exact value of tangent pi over 12. Now, you can certainly work a problem in radians, but you may find that it is easier if you will go ahead and convert that pi over 12 to degrees and work the problem in that manner. So what I'm going to do is I'm going to do that conversion real quick. I'm going to take pi over 12. Now, how do you convert a radian measurement to degrees? Remember that you multiply by 180 over pi. And so you'll see that your pi's will cancel here. You're left with 180 over 12. Which is going to equal 15. And so you could look at this problem as being a problem asking you to find tangent of 15 degrees. Now, we have a couple of different options for tangent of 15. We could do, just kind of thinking about my first quadrant angles, I could do 45 minus 30. I could also do 60 minus 45. And so we do have some choices there as far as how we want to proceed. One thing to keep in mind is that your tangent values, the tangent of 30 is, I'm going to go back up here to my chart and let you take a look at that. The tangent of 30, when I rationalize it, is square root of 3 over 3. All right, my tangent of 60 is here. So if I have a choice between using a 30-degree tangent value, which is a fraction, or using a 60-degree tangent value, which is not a fraction, I usually want to go with the one that is not a fraction. Now, either one will work, but using the fraction is going to mean that your simplifying is more involved. And so you may find that it is easier to use the 60 versus the 30 in your calculation. So I'm going to eliminate this first one because it has tangent 30 in it, and I'm going to go with the second one. And so I'll say tangent 15 can be written as tangent 60 minus 45. All right, so let's go back to our formulas and let's select the right formula. All right, so we're doing a subtraction, so we'll be on this bottom formula. We're going to have 60 for our U and 45 for our V. And so again, I would be plugging in. Everywhere there's a U, I'm going to put a 60. Everywhere there's a V, I'm going to put a 45. And I'm going to go back and work this out. So we will have, I'm just going to write that formula down, tangent 60 minus tangent 45. And on the bottom, we're going to have 1 plus tangent 60 times tangent 45. All right, so we've already seen from our chart that tangent 60 is square root of 3. Tangent 45, you can check back and see that that is equal to 1. So we're going to have minus 1. On the bottom, we're going to have 1 plus, and we have tangent 60 again, so square root of 3 times tangent 45, so times 1. And so our final answer will be square root of 3 minus 1 over 1 plus the square root of 3. Now, you may have seen in other classes that we are really not supposed to have a radical left in the denominator of a fraction, and we're supposed to multiply by the conjugate in order to remove that radical out of the bottom of the fraction. However, in this case, because that algebra is so involved when we go to remove the radical from the denominator, we are allowed to leave it as is. And so you will often see this type of example written with that radical left in the denominator of the fraction. Now again, we could check it by plugging these values, the original problem and also the new answer, into our calculator and make sure that we get equivalent decimal values. Okay, so we're going to look at one other quick example before we end this part of the chapter. We're going to be asked to find the exact value of, and at first glance, this problem looks more difficult. We're asked to find the exact value of sine 80 times cosine 20 minus cosine 80 times sine 20. However, if you recognize that as part of one of your formulas, it becomes not such a difficult problem to work. So I want us to look at this in reference to our formulas. So notice that this goes sine and then cosine. So I'm going to go back to my formulas for a second, and I'm going to look at which ones go sine and then cosine. Let me get back to where I want to be. Okay. All right, so let's look at these formulas just for a second. And we notice that the ones that go sine and then cosine are the sine formulas. So I know that it's going to be one of those two. All right, let me go back and take one more look at that problem. Notice that in the problem we have a minus in between. And so that helps me identify the formula that I'm using as this formula. And so what they are giving me in this problem is they're giving me the right-hand side of the formula. So I'm just going to write it here for us so that we can see it a little bit better, now that we know which one we're using. All right, so this is the formula, and the problem was like this. They said sine 80 cosine 20. And then they said minus cosine 80 sine 20. So you can see that it's an exact match to the formula, except that our u value is 80 and our v value is 20. Okay, so I'm going to go back to the problem and I'm going to say that this is equal to this, sine 80 minus 20. And let's then continue working. So 80 minus 20 is 60. And sine 60 is one of the values that's on my chart, on my unit circle. And I can find that that's equal to square root of 3 over 2. Okay, so actually we take this problem that looked pretty difficult to begin with, and if we can recognize it as our difference identity for sine, then we can work it very easily.